All right, hello, welcome back. So in the last long video, we discussed how we can use relative motion analysis to find the velocities and accelerations of arbitrary points on a body that is undergoing general motion. So for summary, I have shown the result for the velocity here. V of b, arbitrary point, is equal to velocity of a known point, like A, plus omega cross r, the relative velocity of b with respect to A. And for the sake of this video, we will only focus on velocities. Nothing I say in this video or in this section can work for acceleration level equations, only velocities. So that is something to remember. But here we have the velocity equation. Notice what happens if point A is actually a fixed point. So if A is fixed, it means the body is actually rotating about that fixed point A. So you're dealing with a pure rotation. And if that is the case, velocity of A is 0, and you recover the pure rotation velocity equation, which was omega cross, and in the previous case we dropped the b relative to A because we were talking everything was about relative to that fixed point. So we had this, and the equations were very simple. And note that the norm of it, the norm of velocity would be r omega, the direction would be perpendicular. It was a very, very simple problem. Now the question is, can we be lucky and find in a general plane motion, find a point that the velocity is 0 and we kind of recover the same simple, easy to use equations that we had for pure rotation? The answer is yes, and that point we will get to it, is called instantaneous center of zero velocity, or instantaneous center of rotation, or usually very short, IC, instantaneous center. And to demonstrate the utility of this, let's again look at the example of a wheel rolling without slipping. So roll, no slip. And let's pretend I want to find motion of an arbitrary point P. What can you do? Well, the wheel we discussed before is undergoing general plane motion. So you have to find this. Let me put it here. Why is it so far? Finding the movement of point P requires that you first find a point. This point center of the wheel G could be a good point. And then write V of P equals V of G plus omega cross R of P relative to G. And in that case, actually, you don't know V of G itself. So you have to either use the notion of dependent motion that we had before. So it is a lot more involved. But I want to draw your attention to this no slip condition. No slip means that the point on the wheel that is attached to the ground does not move faster or slower than ground. In other words, the point, let's call it point IC, on the ground, at this particular instant, has 0 velocity. And if we accept this, then all of a sudden, I can write same equation omega cross r of p relative to this point RC now. And this point on the ground, the contact point, has zero velocity. And v of p becomes just a pure rotation about this point at this instant. So I can find the vector, the position vector, and find v of p. And at this instant, actually, you can do it for any arbitrary point. So as long as you draw the vector, all of these are going to be velocities perpendicular to the line connecting them to this instantaneous center, and the magnitude of the velocity will be just the distance times the angular velocity. So actually, if I want to be better, this one has to be slightly longer because it has a larger distance, and so on. And one other point that is on the body is the center, v of g. The distance is r. And using this concept of instantaneous center, we can recover v of g is just r omega. And it is perpendicular to this direction of r, so it is a horizontal velocity. Using this notion, I recovered what we calculated before using Feynman's algorithm. Okay, I hope I made the case clear that if you can find a point on a body that has zero velocity, your calculations of velocity will be significantly simpler. All you need to know is the direction and the distance to that point, and you're all set. Now, the question remains, can you be lucky to find this? Well, in the example of the wheel, yes, you use the information that there was no slipping and use that to find this instantaneous center. But can you be equally lucky in other cases? And the answer is yes, you can usually be lucky. So a few remarks on this instantaneous center. The good news is it exists. It exists for any rigid body undergoing planar motion. You can always be sure that there is a point that has zero velocity. For planar motions, it is also unique. So you can always be sure that you can find it, and that is the only one. The IC can be on the body, on or off the body. It could be anywhere. You don't know. Well, not that you don't know, you can calculate it, but it could be anywhere. What else? Oh, a good example, kind of not example. Example? Yeah, let me show it here. So for instance, if, let me see what I want to draw. If velocity of A is like this, velocity of B is like that. In this case, oh no, that's not a good direction. You can find a point IC. If you have the velocities, you can find it. We will talk about how to find this IC in the next video. But it could be outside the boundaries of the body. But you can always find it. One special case is when the body is undergoing in pure translation. You can still argue that the point exists. So you have a body. Everything is moving with the same velocity. And in that case, you can say IC is at infinity. It is far, far away, such that the distances are so big that essentially all these velocities are perpendicular to that line, and you reach infinity. Let me see, what else can I say? Oh, one other thing. IC is a perfect, excellent concept in planar motion. When you are dealing with 3D movements, things become more complex, that you don't have kind of necessarily just a point, but you have a certain kind of axis that the body translates and rotates about that axis. We don't worry about that. In planar motion, all of these, the points that I have mentioned so far, hold. One very important piece here, velocity of IC by definition is 0. But acceleration of the same point is not necessarily 0. So consider this point on the wheel, this point I called it IC. It is a point that as you draw its motion, it is, if you look at that particular point on the rim of the wheel, it is further up from the ground, it comes down, touches the ground, and goes back up. So that point on the wheel actually undergoes a rather complex motion itself, and it has non-zero accelerations, even at the time the point is touching the ground. But the only thing that we can say is at that particular point, its velocity is 0. Therefore, I can use it as an instantaneous center and do all the good calculations. Nothing is certain about the accelerations. And yeah, here is a fun, not paradox, but paradox looking thing. So I have a wheel rolling without slipping. That is an ugly wheel, sorry. Then at a later time it has moved forward, it is here. So I say IC is here now. And as the wheel rolls forward without slipping, the IC goes here. So it has displayed some amount. Now answer this. If the velocity of a point is 0, how does it move? IC by definition has 0 velocity, but here it moves. The point, it's not a paradox. Nothing is broken in physics. The thing is, let me actually color code this, delta S. Make this red. Red IC and blue IC. The point is, let's call it red IC, and maybe this one green IC. These are two different points. Red IC at a previous time was here. This was, I call it red IC. And the green IC at a later time moves up and comes here. What is moving and translating is the locus of all ICs over time. A point becomes IC and stops being IC, and another point becomes IC and it stops being IC. So the trajectory of all these different ICs across time move, but the instantaneous centers, by definition, at a particular time that they are instantaneous center, have zero velocities. So that is something to remember. And this actually has a name. It is called centroid. The trajectory of these ICs is called centroid, according to textbook. Okay, so that is all I wanted to say. And as a piece of advice is, whenever you're dealing with at least velocity level problems, your best course of action is first see if you can find an instantaneous center somewhere in the problem on for your bodies, and then that simplifies the problem a lot. And how to find it, find an IC, is what we will do in the next video. Right now, we only know it exists and we should be able to find it. How to find it comes next. So I'll see you in the next video.